If the universe is a game, then we, Earth's civilization, might have lost the most important part at the very beginning, the instruction manual. Because when we analyze the question, why is the universe so silent? One of the most disturbing answers emerges. Silence is the rule. That lost manual might have had only one core directive, written in red. Once discovered, eliminate immediately. And not only have we not hidden ourselves, we are using every method at our disposal to shout to the entire universe, we are here. So, when will the program responsible for cleaning up the eliminated players come for us? This chilling thought is one of the darkest answers derived from the Fermi Paradox. But to understand how we arrived at this precipice, we must first return to the beginning and see how we started our search in this cosmos, a search born of relentless hope. Hope is a stubborn thing. It compels us to start the search in our own cosmic backyard, where the clues are within our reach. On Mars, a six-wheeled, semi-autonomous geologist named Perseverance is diligently exploring the Jezero crater. This isn't just any crater. Billions of years ago, it was a deep, calm lake fed by a winding river, which built up a magnificent fan-shaped delta, a geological feature known on Earth for its ability to preserve organic material. Here, the rover drills into ancient Martian rock with its robotic arm, sealing pristine core samples in hypersterile titanium tubes, hunting for complex organic molecules, the chemical biosignatures of life. Its SuperCam instrument can vaporize rock with a laser to analyze its chemical composition from a distance, while other instruments scan the subsurface for signs of past water. These carefully cached samples are the first step in a breathtakingly ambitious plan called the Mars Sample Return Mission, a multi-stage, multi-spacecraft endeavor to one day launch these pieces of Mars off the planet and bring them back to Earth for study in our most advanced labs. So if we do find evidence of ancient microbes there, it will be the beginning of a new chapter in the story of life. Then, our gaze turns further out, to the frigid, majestic realm of the gas giants. NASA's Europa Clipper mission is being prepared for a long journey to Jupiter's moon, Europa. A world about the size of our own moon, but wrapped in a global shell of water ice, miles thick, scarred with vast, rust-colored cracks and towering ridges. The real prize, the Holy Grail, lies beneath that ice. We know this because of compelling data from the Galileo probe, which detected a strange, induced magnetic field around Europa, a field best explained by a planet-wide layer of conductive material. Salt water. The moon's surface shows what planetary scientists call chaos terrain, jumbled, tilted blocks of ice that look like frozen rafts on a disrupted sea, suggesting the shell has fractured and shifted. On a liquid layer below, this hidden ocean, kept liquid not by the sun, but by the immense gravitational push and pull from Jupiter, a process called tidal flexing that heats the moon's interior, holds more water than all the oceans of Earth combined, perhaps by a factor of 3. And deep on its seafloor, in total darkness, there could be hydrothermal vents, spewing heat and chemical nutrients, just like the ones on Earth's ocean floors, where life may have first begun, powered by chemistry, not sunlight. It is, by all accounts, one of the most promising candidates for existing, albeit likely microbial, life in our solar system. So, the idea that life originated elsewhere is not fantasy. It is a methodical, serious scientific inquiry. But the hope of our local search stands in stark, almost mocking contrast to the dead silence of the entire galaxy. This contradiction was first clearly articulated during a 1950 luncheon at Los Alamos by the physicist Enrico Fermi, who, after listening to discussions about interstellar travel, asked that famous, disarmingly simple question, where's everybody? This is the Fermi Paradox. It's formalized in a framework called the Drake equation, a probabilistic argument used to estimate the number of active, communicative civilizations. It multiplies a series of factors: the rate of star formation, the fraction of those stars with planets, the number of habitable planets per system, the fraction on which life actually appears, the fraction that evolves intelligence, the fraction that develops technology to communicate, and finally, the length of time they release detectable signals into space, the L variable. No matter what conservative numbers you use for the early factors, the result always points to a galaxy that should be, or should have been, teeming with civilizations. But reality is silence. the L variable, the lifetime of a civilization, might be terrifyingly short. One explanation for this paradox is humbling and perhaps lonely: the rare Earth hypothesis. It argues that while simple microbial life might be common, the journey to complex, intelligent life is paved with nearly impossible obstacles, a series of great filters that we luckily passed. It requires an unbroken chain of life, stretching across geological time. For billion years, on Earth, surviving every gamma ray burst, every supervolcano, every global ice age. It may require a planetary feature as specific as plate tectonics, which acts as a global thermostat, regulating atmospheric carbon dioxide and preventing runaway climate change over eons. It may require a solar system just like ours, a large planet like Jupiter, acting as a cosmic bouncer, ejecting dangerous comets and asteroids from the inner solar system. It may require a large moon, like ours, formed from a chance giant impact, to stabilize our planet's axial tilt and prevent wild, life-extinguishing climate swings. Perhaps the combination of all these factors is so incredibly rare that we are the first, or maybe even the only one, to have won this cosmic lottery. This idea transforms us from irrelevant dust into the most profound, and perhaps the most responsible, one and only in the universe. Of course, there are darker explanations. The game rule we mentioned at the start. Its academic name is the dark forest hypothesis. It suggests the universe is not a friendly neighborhood, but a dark forest, operating under a grim set of axioms. First, survival is the primary need of every civilization. Second, every civilization grows and expands, but the total matter in the universe remains constant. This makes every other civilization a potential existential threat. And since you can never know the true intentions of another civilization across vast distances of space and time, are they benevolent, or are they hiding their true power? The safest course of action is to remain perfectly silent and hidden. Any civilization that reveals its own location immediately becomes a target for all others, and faces the risk of being eliminated as a precautionary measure. From this perspective, the great silence is the sound of all survivors holding their breath. And not only have we not held our breath, we are actively shouting into the forest. And on one occasion, it seems we heard an echo. August 15th, 1977. The Big Ear radio telescope at Ohio State University detected a powerful, narrowband signal. For a full 72 seconds, a torrent of radio waves came from the direction of the constellation Sagittarius, peaking at over 30 times the background noise of the galaxy. Its wavelength was 21 centimeters, profoundly significant. This is the emission line of neutral hydrogen, the most common element in the universe. Scientists had long theorized this would be the universal hailing frequency, a logical, obvious choice for any civilization wanting to make contact. It was a beacon, shining at the cosmic watering hole. When astronomer Jerry Emmons saw the data printout days later, he was so stunned by how perfectly the signal matched predictions. He circled the alphanumeric code, 6EQUJ5, and wrote a single word in the margin. Wow. The wow signal has never been detected again. All subsequent searches have found nothing. A fleeting, tantalizing mystery. Blink, and you might miss it. The universe is noisy. Separating a message from the cosmic static is a monumental challenge, the ultimate needle in a haystack problem. This is precisely why projects like Breakthrough Listen exist. Using the world's largest steerable telescopes, they are scanning 1 million nearby stars and the 100 closest galaxies. The sheer volume of data is staggering, petabytes, far too much for any human to analyze. So they are using artificial intelligence, training machine learning algorithms to sift through the noise, hunting for techno-signatures. Not just simple pings, but perhaps evidence of industrial pollution in an exoplanet's atmosphere, or the waste heat from a stellar-scale engineering project like a Dyson sphere. And it's working. Peter Ma, a student at the University of Toronto, developed a new algorithm that reanalyzed older data from the Green Bank telescope. It filtered out Earth-based interference and identified 8 previously unnoticed signals of interest. None of them are confirmed alien messages. They are candidates awaiting further verification, but they prove our tools are getting sharper. We are learning how to listen. As we continue to search the skies, straining to hear the faintest whisper, we still face the fundamental question from the beginning. Should we continue to shout, hoping to find friendly companions? Or should we fall silent immediately, praying we haven't yet been found? By the rules of the game? We don't know. And this is, perhaps, the greatest gamble a civilization can make. The stakes could not be higher. This great exploration has only just begun.
Okay, if you too are fascinated by these ultimate cosmic mysteries and wish to gaze into the abyss with us, be sure to like, share, and subscribe, because the next message we receive might just decide our fate.